合租, and he is upcoming job, which he will
automatically learning. So first, how does in order to use the software code, function in the outcome library, as the is licensed. Oftentimes, program recursive as what will a programmer react when he knows programmers do not verification tools in their work. Sure, software will first define, for example, a data to manipulate the data structures. So in the also calls a recursive function flight, which the flat function implementation is not interesting. What this code contains no program assertions. It contains cannot inform any useful if implementation is correct. The element function any element from the input tree T is equal to forward order traverse of the output list L function is as what the programmer expects. Of the input tree T is equivalent to a verification tool because the programmer will be not programmers write tests to require specifications. So clearly there's a gap. Specification can usually be discovered from that can automatically discover software test. algorithm instead of a programmer to ensure formal specification understood and verified. Get one for free. We pay the cost of testing inputs, showing a wide hypothesis specification. You can refine the previous solution with new a set of program tests, but this test might even be false. So in this talk, specification learning. Step of our learning algorithm is to identify and extract with the sample space available to it. For the element function, it takes an input. These are mainly about containment and reachability. For example, T containing 5 is considered a for this structure T is a reachability feature. Then we have the tree parent left child. Child of 4 is considered the true reachability for input tree T. And in the example 5, 'If U comes from the left subtree and V comes from 'the right subtree of the containment and reachability can also be applied to this. Feature for a list L checks for arbitrary 5 is reachable from 3. So these two are containment and reachability features define the hypothesis reachability specification functions. And in any function from this hypothesis, the variable U is quantified. Input features over the terms of the tree contain We also over the output list L, we want to by observing the truth of the input, show a Boolean combination of the input features. For example, candidate specification to imply. And indeed, we can associate U and V, or V is a Rothschild of U, or then the reverse is also true. More importantly, this specification is formal. Structures should not be hard-coded into the system. Feature extraction for arbitrary user-defined subtrays. The relation between the left child of U in the tree T. So we can associate U in the tree T if and only if U is the defined in its left subtrays or recursively defined. Second recursively defined subtree suggests the definition relations tailored for the design of the data. Includes input binary tree T and feature space. The feature space are about containment. Data structure element U and V from the original data structure samples. With many specifications. The algorithm will out features, and here 0 represents the truth feature. For example, when V is assigned to 2, the learning algorithm can still know 1 is definitely a left child of V. 1 is definitely a left child of 2, and 1 is not a right child of from the original data structure samples to reachability samples will not lose any structure information. As we have said earlier, we want to predict the truth of the output features by observing the truth of the input features. So it is nature to use an output feature to partition the sample space into two sites, one of which satisfy the output feature. So these are the positive samples for the feature. The other samples does not satisfy. So these are the negative samples for this particular output feature. The goal of the learning algorithm classifier that can separate all the positive samples to this particular output feature with features. If we are successfully inferring such a classifier predicate psi, we also obtained a candidate hypothesis specification. The classifier predicate psi is logically equivalent to the output feature. Classifier predicates and the output feature predicate capture the same subset of samples from the sample space. To learn a classifier predicate to separate all the positive samples from all the negative samples as an optimization task to overcome overfitting, we flavor the simple specification to a complex one. We want to minimize the number of features used for building a classifier predicate. To this end, we can build a constraint system. The constraint include for each positive samples, it must be separated from all negative samples by selecting some features. The goal of the constraint system is to minimize the number of selected features. We can use highly optimized constraint solvers to solve this problem. In our case, the solver might be able to conclude that we can use just 3 features out of the total 8 features to classify the samples. Positive samples and negative samples all evaluated features. After we get to know the classifier predicate, we also obtained the truth table for the selected features. The truth table should accept all the positive samples and reject all the negative samples. We can happily apply a textbook algorithm to translate into its logical formula. And finally, we derive the hypothesis specification we desire for the element function. The traverse of the input string T is equivalent of the output list L. At this point, it's clear that our analysis can synthesize relation if and only if specifications relating program and output features, which are nice. But what about a classifier predicate from these samples? This problem occurs when we have coinciding and conflicting positive samples and negative samples in the sample space. The no classifier predicate exists in the hypothesis space that can separate our solution to this problem is to learn if or only if relation specifications that still relate program input features to program output features instead of learning an exact if and only if specific learning algorithm are presented in our paper. Learning algorithm into the whole verification framework. Given a program P, component analyzes the data structure definitions inside the program and outputs reachability and containment features tailors the uses of data structures inside the program. Executes the program and returns a number of input and output samples for in the program. Initially, we can use quick check to collect a lot of them. Then these features and the samples are given to a learning algorithm for hypothesis. In our paper, a verification system that can validate such for data structures. The verification system is based on a refinement type system. So verification condition generation reduces to subtype checking. So our approach can also be considered as if the presence of verification failures, the learning algorithms can specifications from more representative test inputs obtainable from verification counterexample. The question here is whether this testing, learning, and verification loop can eventually. This loop will not converge when the learning algorithm synthesizes inductive, but a non-inductive invariant. A non-inductive invariant cannot be verified by the because it is a true invariant. So in this case, this testing will get stuck. Invariant look like. Consider the element function composed with a minimum number of features. Samples happens to be a non-inductive claims for arbitrary data structure element U and V. U in the output list L, then U and V must be contained. This invariant is non-inductive because the reachability relation between U and V is not captured in this specification. It is a 2-over approximation of an inductive invariant. Our learning algorithm will never produce such a two-course over approximation because it can't use the two containment predicate T containing U and T containing corresponding positive samples and negative samples to that particular output feature predicates. The existence of the negative samples enforces the learning algorithm other predicates to learn a more but stronger specification precisely the reachability relation between U and V from the if V can be reachable from U in the output list L. Because the learning algorithm will never produce a true invariant, so any solution from the learning algorithm is either an inductive invariant, which definitely leads to counterexamples. We implemented in this data-driven framework can eventually inductive specification in the hypothesis space defined in a given program. Although our analysis can synthesize very expressive reachability, we still need to know other kinds of data structure properties. For example, for a tree, programmers may need to know whether T implements a binary search tree. We can easily adapt our analysis specifications. Additionally, if T is a red-black tree or AVL tree, then the program whether T faithfully implements a balanced tree in terms of the height of the tree. Our analysis can synthesize such numeric specifications as well. The paper, the above two examples shows that the general framework for doing. We implemented our data-driven called deorder. Deorder is implemented on top of deorder. Programmers just write code as euro. The tool can automatically report specifications in terms of refinement types. The program needs to provide any annotation. We tested challenging benchmarks, including Okazaki's functional stack and queue, list routines, including list sorting, including classic list sorting algorithm-based set implementations, and useful heap and tree implementations, such as AVS tree or red-black tree, and some widely used Alcama libraries. We synthesize a high-quality specification for all these benchmarks. Data specifications and numeric specifications proving that balanced and they are BST. In our experiment, we find that our verification is very fast. For example, for the most challenging benchmarks, the red-black trees can be verified in just 2 minutes, and the AVL trees can be verified in just 1 minute. Most benchmarks can be verified in less than 13 seconds. Our experiments also demonstrated our hypothesis program specifications can be synthesized from a small number of tests. With 100 samples, AVS tree can be verified with less can be verified with less than 20 samples. There are some unique features of our approach. First, we do not require programmers to provide any annotations, pre and post conditions. Our approach can guarantee high quality specification synthesis. Learning algorithm can synthesize the strongest specification up to a hypothesis domain. Our approach can also guarantee strong. There always exists a test input to refine an unverifiable specification. Demonstrated the usability of our approach in some really challenging and real-world. Yeah. Thank you for your attendance. So that's all I would like to share. Specification synthesis framework.
If you have questions, affiliation.
So when the verification fails, how do you tell the specification or from the implementation?
So we think every implementation, even a false. So the goal of the system is to only produce a specification. The program is additionally equipped with some program assertions, like what you have synthesized the specification to prove the user provided annotations.
Buggy programs?
Yeah, we tried some buggy programs. So in this case, by just looking at the specification, then the normal user can already discover that the implementation is not correct because the code is not as the programmer as was the programmer.
You mean the system will come up with a specification makes sense to the programmer,
Right,
and the programmer.
Right. Yeah. So for example, you have a list program, then the specification from the reverse program shows reversed.
Okay. Thanks.
So I didn't get whether you were Illinois. So I was wondering whether you guarantee that you will learn the strongest inductive.
Yes.
I wondered whether you consider that given that maybe in your hypothesis space there is the strongest inductive invariant may not be explained. It might actually be better to an invariant, right, rather than an inductive invariant.
But if our invariant is not inductive, then our system are not able to verify it. So that is the reason why
that might be okay. Depending on the application, it might be okay not to verify it, right? But
sure, yeah. So
but it might be a more useful invariant, though it's not inductive.
yeah. So one learning algorithm that learns the minimum specification in terms of the number of features used to build a classifier. So if we replace learning algorithms, then we lose this convergence guarantee. Still propose some good specifications. Complexity will be even lower. So it will definitely make sense.
All right, let's think again.